I just confirm you can hear me.
Yes.
Yeah. Okay, great. Oh, I need to fix my settings. One moment. Sorry, I'm gonna have to reconnect briefly. Be right back.
No worries. You can tell that we're a workplace that usually uses Teams.
Okay. Let's make sure that worked.
We are seeing screen.
Okay, great. These present for first realization implement serializer for some reference material there. So diving right in, here's kind of a refresher. Uh, Lydia's great tutorial from yesterday in chat used to create a file read. So, and just a writer, I write hello, and then I read it back in. Um, Actually dictates how hello is printed, and the answer is serializers. Um, so its basic definition, serialization can be defined as the process of turning objects into bytes of text so that you can store them on a disk or transmit them over network. And deserialization would be the first, taking bytes of text and turning them into objects. Apple serializers are records that particular API that does how the model will read or write these values. And it could be primitive types like ints or strings, but also records, classes, arrays, and any other data type in Chapel. Generally, these are implemented using some very low-level I/O methods that do not invoke serialization, but you can also invoke other serializers, which can help with code reviews. Serializers allow for the invocation of certain methods on classes and records that allow the implementers of those types to customize serialization. For writing, this involves a method called serialize. For reading, you can either write an initializer or a method called deserialize. We'll go over those later in more detail. And I'll say that over the course of this tutorial, we're not going to be able to go into complete depth on every aspect of serializers. I would refer you to the IO serializers tech note that I linked in the Zoom chat. And if you have any further questions. So there we go. Um, so the file reader and file writer types have a default serializer implementation. Um, this type is suitably called default deserializer or default serializer, and it is defined in the IO module. And uh, the methods for creating a file reader or writer use these as a default argument. So when you're saying file.writer, you're really invocating or you're really using a new default serializer as the argument. And similarly, with a reader, you're using a new default deserializer, passing that in by name. Of course, Chapel has other serializers. In particular, we have a JSON module, and we also have a rudimentary binary format. The binary serializer and deserializer can be found in the IO module, and the JSON implementation can be found in the JSON module. We do have some others, like the YAML module, but they are currently unstable. So as an example, using what we just learned about creating file writers, here we have a program that uses the IO and JSON modules. We have a very trivial record with a single field that is an int. We start off by opening a new file using an integer descriptor. That's assuming we're on a POSIX system, by the way, and that will open standard out. And then we call the writer method on that file. We pass in a new JSON serializer, and we get a file writer back from that. And then finally, we use that writer to print that record out to standard out, and that prints a JSON object with the name value pair of X and 42. That's not the only way to get a file writer with a particular serializer. We also have a method called with serializer that you can invoke on an existing file writer. And similarly for file reader, you use a method called with deserializer instead. Let's use the with serializer method to simplify a previous example. So instead of creating that file within a descriptor, let's reuse the built-in as variable from the module. On the variable, let's invoke with serializer and just pass in a new JSON serializer. And this allows us to just do the exact same thing as before. We print the record the same way. It's just a little more convenient. So expanding on this example, let's do both serialization and deserialization. Instead, we'll open a memory file, or open a file in memory, I should say. We will create a writer by passing in a new JSON serializer, create a record that for the file, and that'll print the JSON object with the name value pair of data and 42. And then we call the reader method on that file. We pass in a new JSON deserializer by name to the deserializer that we're going to call the .read method and pass in the type X. And that will tell the IO module that we want to create that new type by reading it in. And this brings us to our first exercise, where your mission, should you choose to accept it, is to write a list as JSON and then read it back in. I have some starter code on the slide here. In chat, just before this tutorial started, I posted a link to the GitHub repo where you can start off from the exercise1.chapel file. And I'll give people a minute or so to try that out for themselves. It's also a good time for any questions if anyone has any. And as a reminder, we're working with the methods .writer and .reader, and we're passing in a new JSON serializer or deserializer.
Benson's got a question. How does this compare to protobufs and other serialization libraries?
So that's a good question. I think every serialization library has its own quirks. I think in Chapel, Uh, I guess I don't know how to compare it directly to protobufs, but I think in Chapel it's a bit broader in that you can implement all kinds of serialization formats. All right, go ahead and give you half the solution here. Part A, writing this out to a file, create a writer, pass in a new JSON serializer by name to the serializer argument, and write it out in flushing the file is a good practice in this instance. Give this another few moments. And the rest of the solution, again, we're invoking the .reader method on a file. We're passing in a new JSON deserializer to the deserializer formal. And then we invoke the read method. We pass in the type we want to read, which is a list of integers. And then we write that out. All right. Any questions on that exercise? Okay. So diving into some of the more interesting stuff, which is the customization of how types are serialized. Um, Now we're getting into kind of the broader serialization API in Chapel, and that can be broken into roughly three pieces. So the first piece is more relevant for implementers of serializers, and these are the methods called by IO to hand off control to that serialization implementation. It's the second two pieces that we're most interested in at the moment. Um, One is that methods that a serializer can invoke on user types to allow for customized IO. And the last piece is the group of methods that a user-defined type can invoke on a serializer to perform what we're calling format agnostic IO. And format agnostic IO concerns the serialization and deserialization of certain kinds of abstract types. And for example, many formats have their own notion of a list or a map. And a portion of the API is devoted to each kind of abstract type, which we'll get into detail later. Um, so for user-defined serialization on a given type, the user wants to implement a serialized method that will be invoked on classes and records. And this is defined by the write serializable interface that Daniel alluded to earlier in his presentation. So this is a method called serialize. It takes the first argument, which is named writer, and accepts a generic file writer. And then the second argument is a serializer that is passed by the ref intent. And that's in the event that the given serializer maintains some internal state that might need to be modified over the course of serialization. And finally, this method throws, um, as all IO methods do. And the serialize method can be implemented for any serializer or specialized by type. So if I want to implement this for any serializer, I could write something like the example on the slide here. So here we have a type called myType. It specifies that it implements the write serializable interface, and it just has two fields, a name that's a string and an ID that is an int. In the example serialize method here, it just writes this with angle brackets. It says it's a myType, and for whatever reason we say it just wants to print the name. And this will apply for any and all serializers that invoke or that try to serialize myType. So this brings us to our second exercise, which is to write your own serialize method for this counter record. And we want to print this record as an integer rather than a record. And we can do so by implementing the serialize method. So this program, as is, will print the counter like a record in Chapel, which means it will print the field name, the equal sign, and the field value, and we'll wrap that in parentheses. But really, we just want to print 4. So I will give people a minute or so to try this out, and this would be exercise 2.chapel in the GitHub repo. And any questions on this section so far? So a preview of the solution. Again, this is the signature of the method that we'll be implementing. It's called Serialize. It takes a writer and a serializer by ref. And from here, the rest is pretty trivial. You can probably guess we're just going to write the count field. Any questions on this mini exercise? All right. So moving forward, as I mentioned before, you can write serialized methods for any and all serializers, or you can implement a serialized method for a particular serialization type. So here we have an example of implementing a serialized method specifically for JSON. And building off of our previous my type record, let's say we wanted to instead write this out as a proper JSON object. In this instance, we're using the write literal method to literally write the opening part of this object with the curly brace, the name, and the semicolon. Write literal is special in that it will bypass serializers entirely and write the string as is. Otherwise, if we used writer.write here, it would print as a JSON string and escape the quotes in that string as is, which is counter to what we want. So once we've written that literal, we can call writer.write with the name field and write that as a proper JSON string, which is what we want, and then wrap that up by calling write literal with a closing curly brace. Of course, this is a bit tedious, prone to errors, and is essentially reinventing the wheel by having to comply with the format specifications explicitly. And really what you want is a way to have the serializer take care of that for you. And that's where the format agnostic API comes in. So serializers and deserializers have 6 type kinds that they can serialize. These types are classes, records, tuples, arrays, lists, and maps. And to begin serializing one of these types, you're going to invoke one of the 6 start methods associated with that type kind. So this is a big grid here. So when you invoke one of these start methods, it will return a record with methods for that particular type kind. So for example, when you invoke start record, that's going to return a value that you can use on which you will invoke the write field and record methods. Additionally, these start methods will accept a file writer and often a size argument to indicate, for example, the number of fields or elements in that type. We're not going to go through every single method here, so you can breathe a sigh of relief. I would refer you to the IO tech note that I mentioned before if you want to learn more about the particulars of these various methods. But let's dive into an example, and let's, instead of the JSON example from a couple slides ago, let's use the format agnostic API to write this as a record with just one field. So here's a reminder of our kind of contrived my type implementation. Has two fields, one uh, named, and it's a string. The other is an ID, and that's an int. We have our familiar serialize signature. It takes a writer and a serializer by ref, and it throws. And we're going to start off. My bad. Let's get the slide there. So we start off by invoking the start record method on the serializer, and we pass in our writer. We pass in the name of our type being serialized in the event that the serialization format cares about that. And then we pass in the number of fields we're going to write, which in this case is just one. And start record returns a value that we store in the field sir. On sir, then we invoke write field. We pass in the name of that field, which here is just name, and we pass in that field's value. And finally, we call end record. And down below, we create a new my type. We call it Sam, and we give it an ID of 1, but we don't want to print the ID. And that's what our serializer does. So next we invoke write line on standard out, which by default we use the default serializer, and that prints the first line of the example in the darkly colored box at the bottom there, which is how we print normal records in Chapel. We print the name of the field, an equal sign, and then the value of the field, and we wrap that all in parentheses. And then in the second example, we use with serializer to get a JSON version of standard out. And then writing that out, we get a JSON object with a key value pair of name and Sam. So that's another example with the list collection of methods. And this is something you can explore more deeply in demo7.chapel from our GitHub repo. So let's say we have a record my list, and if you'll give me some room here, let's just assume it implements all the things you would need for a list. Among those things, it has a num elements method that returns an int, and it also has an iterator .these that returns the integers in that list. So if I wanted to write a serialized method for this list, I would start by implementing our serialized signature. It takes writer serializer by ref and it throws. The next thing I would do is invoke the start list method on that serializer, and I would pass in the writer and the number of elements that I wanted to write. And if, for example, we were doing this in JSON, this is when the opening square bracket would be written. Then I'm going to iterate over every element in this list. And then I'm going to invoke write element on the helper object we got from start list. And I'm just going to pass in the element we want to write. If this were in JSON, this would write the comma if necessary, followed by the element. And then lastly, we call end list, which in JSON would write the closing square bracket. So deserializers also provide the same group of methods for the same type kinds, except now we're reading instead of writing. Just like the serializer case, each start method will take a file reader and return an object with methods that support reading that particular kind of type. I should note here that each of the read methods accepts either a value by ref or by type, and that matches the behavior of kind of the top level file reader.read method. So that exists to support either reading a value in place by passing by ref, or by creating a new value by passing by type. So users can override the default in place deserialization behavior with a deserialized method. This deserialized method is defined by the read deserializable interface. This method is called again deserialize. It takes a reader and a deserializer by ref and it throws. I should also note here that the deserialize method has a ref this intent, and that is the ref keyword between proc and t there on the slide. And that indicates to the compiler that this method will mutate the type. And again, this intends to provide the behavior for the version of file reader.read that accepts values by ref. So as an example of using this, let's say we wanted to read in that abstract type that we wrote. And for more here, you can look at demo8.chapel. So I'm implementing our mylist record. It was write serializable before, and now we also indicate that it is read deserializable. And to implement this, let's assume we have methods like clear and append. So we start by writing our deserialized signature, takes in a reader and a deserializer by ref, and it throws. We start off by clearing the record. That has nothing to do with serialization. We're just reading in place, so we're clearing out the data. We invoke start list on that deserializer, pass in the reader, and in JSON, this will read the opening square bracket and returns a helper object des. And while, so we invoke the has more method on des, which in JSON will check for more elements. And while that is the case, we will read those elements in by int, and we will append those newly read elements to our list. And finally, we call endList on that helper object, which in JSON will read the closing square bracket. For reading, there is also a deserializing initializer that one can implement. And this initializer also takes in a reader and a deserializer by ref, and it throws. In Chapel, it can only throw after all the fields are initialized, though. Future editions of Chapel may relax this requirement, but for now, the compiler will issue an error if you run into this restraint. This initializer is particularly useful for types that cannot be default initialized and requires some sort of initial value. Otherwise, it works the same as a deserialized method. And you'll use the same format agnostic API to do all your deserialization. There's an example of the mylist implementation for a deserializing initializer in demo9.chapel. But I'm rapidly running out of time here, I believe. So let's go ahead and look at exercise 3, which will involve actually using the format agnostic API to serialize and deserialize coordinates as a tuple. So for our starter code here, we're using the IO and list modules. We have a record point that has two fields X and Y, and they are ints. We create a list of points, build that up, and sort of do the thing we've been doing. We open a file, we create a writer, we write that object out to the file, and then we read it back in. But this program, as written, when you write it out, it writes a point as a chapel record, which means it's going to say, x equals 1 and y equals 2, x equals 3, y equals 4, and so on. But really, we want to write this out as a tuple. So we want it to read, parenthesis 1, comma 2, closing parenthesis, and so on. And that is the goal of this exercise. Again, there's some starter code to get you going in exercise 3.chapel in our GitHub repo. And I will incrementally kind of reveal some parts of the solution here as we wait for people to try these out or ask questions. A reminder here, you're going to be looking to implement the serialize and deserialize methods, as well as the deserializing initializer to implement all three. Give it a few more moments for people to evaluate this starter code on the slide before moving on to some of the initial early hints. So here's some method signatures to get you started. So again, we're implementing point.serialize, point.serialize, and the deserializing initializer for the point record. Also take this time to explain that when you add an initializer for a record that previously did not have one, it prevents the compiler from generating a default implementation for that initializer. So you also want to add the trivial initializer I've written here on the slide, which just takes x and y by int and initializes the fields. The IO tech note also has some more in-depth explanation regarding this. All right, the next set of hints. Again, we're going to be using the start tuple set of methods from the format agnostic API. It's going to involve start tuple on a serializer or deserializer, and you're going to use either write element or read element, and then end tuple. All right, so I'll give you a serialized solution. I don't think we have time to dive into the whole thing. So to implement point.serialize, you're going to start with invoking start tuple on the serializer. You're going to pass in writer and the number of elements that are being serialized, in this case 2. On the returned helper object ser, you invoke write element, passing in x, and then another call passing in y. And then finally you call end tuple on that serializer. For the full solution, you can refer to solution 3.chapel in the GitHub repo that I linked earlier. Some final notes on the API here. User types that implement all three methods, that is the serialize, deserialize, and init methods, can use the combined serializable interface instead of listing all three. Additionally, the serialize and deserialize methods on classes must use override. And that is because all classes inherit from the root class, which itself can also be serialized or deserialized. And again, as I mentioned before, implementing the serialize or deserialize method or an initializer prevents compiler generation of all three. And the rationale here is that if you implement one of those, then the user is probably diverged from the default behavior. So the compiler doesn't want to generate the other two and implement something incorrect. So in the remaining time, a couple slides here on implementing serializers themselves. So to implement a serializer, you must implement a method called serialize value on a record. This method accepts a writer and a value by constant intent, and it throws. Serialize value accepts either primitive types or types that have implemented the right serializable interface. Once invoked, serialized value has complete control over serialization, but it is expected to invoke the serialized method as needed. Additionally, to implement serializers, you must also implement that whole format agnostic API that we were going over in the previous section. Again, all that is in the IO tech note for those who want to explore more. For implementing deserializers, we're going to see two methods here. Again, reflecting the nature of file reader.read, in which we have a method to handle types or values. So this first method is deserialize type, accepts a reader and a type argument, and it returns a type, and it also throws. This is compared to deserialized value, which takes a reader, takes a value by ref, be read in place, and it returns nothing, and it throws. These methods accept either types with the read deserializable or init deserializable interface, or primitive types. And again, once invoked, these methods have complete control over deserialization. There's no callbacks to the IO module to deal with. And to implement a deserializer, you must implement the full format agnostic API of the previous section. All right, and wrapping up, just some references for those particularly interested in implementing their own serializers. There are a few modules you can use to learn from. There are a couple standard modules, JSON that we've been using through this tutorial, also the precision serializer, which is sort of an extended version of the default serializer and has some arguments users can pass in to indicate how they want their floating point values to be serialized. We also have an unstable package module, or collection of unstable package modules. I think YAML is the most interesting one. It extensively uses a third-party library for its implementation. We also have a couple of other modules, object serialization, which is a binary format, and we also have the CHPL format module, which is kind of a holdover from pre 2.0 code that attempts to print values as chapel code or chapel literals. And finally, for those implementing their own serializers, there's the test IO serializers directory in the chapel repository, which may also be useful. It contains various stress tests of common serialization cases, and it's pretty easy to plug in your own serializer to test it out. And that's all I've got for serialization. And I think we're on time.
We are just perfectly on time. Thank you so much, Ben. I'll stop the recording and people drop any questions in chat, come off mute to ask, etc.